Right, Kepler's third law is something that causes some GCSE students a bit of grief because it looks complicated, but if I can try and give a few hints here and simplify things a bit. I mean, stated in mathematical form, Kepler's third law will be something like this. T is proportional to A. Okay, so T is the time for one orbit. So we're starting off typically with an object orbiting around the Sun. So that'll be the time for one orbit, and that will be the semi-major axis cubed. Well, A is just the semi-major axis. Okay, in a fairly trivial way, if you think of things going around in a circle, then this would be the radius. But as we know from Kepler's first law, objects will go around the Sun on an ellipse, so it becomes the relevant the relevant quantity here is the semi-major axis. So the time for one orbit squared is proportional to the semi-major axis cubed. So that's stating Kepler's third law as in a mathematical way. Now, from GCSE mathematics itself, to convert a proportionality into an equation, you convert that to an equal sign, and then you multiply by a constant. So as an equation, that would become K A cubed. Okay, where K is a constant. And if we do a bit of algebra, T squared over A cubed equals K. Okay, so that's what that is saying is that ratio, the time for one orbit squared over the semi-major axis cubed, that is a constant for all objects which are orbiting the Sun. Okay, we're starting off talking about objects orbiting the Sun. So this ratio will be identical for all objects orbiting the Sun. So therefore, you can set up an equality. You work out the ratio for one planet, work out the ratio for another planet, and then equate them together to form an equation. We can have something like this. T1 squared over A1 cubed equals right. So if you know three of these quantities and you want to find out the other, you start off from an equation of this form. And a little hint is that if one of the unknowns is A1 or A2, you don't really start off with an equation of this form. You can just flip them over. So you'll have something like this. That would be much easier if one of the unknowns is an A. So for example, I'm running out of space here. If it was A1 that you wanted to find out, if you knew what T1, A2 and T2 all were, then you could set it up originally like this, and then just do a bit of an alteration. And there you are. If you know these three quantities, you just stick them in the right hand side, do a bit of arithmetic, possibly use your calculator, and out drops the, what will drop out will be A1 cubed, which you then can take the cube root of. Alright. So that's not too difficult per se. That'll take you quite a long way. Now, if I was to look at it in more rigorous manner, this T squared over A cubed, well, that does equal a constant, but the actual constant stated more fundamentally, is m minus m over 4. Okay. Where G is the gravitational constant, which is the same everywhere, obviously 4 pi squared is the same everywhere. M is the mass of the object that is doing the well, M is the mass of the object which is at the centre of this particular system we're looking at. So if we're looking at the solar system, M would be the mass of the sun, and M would be the mass of a planet or comet or whatever we're considering. Now, a general rule here is to say, okay, the mass of, say, the planet, a mass of a planet in relation to the mass of the sun, this mass will be so small that we'll just forget about it. To a very good approximation, we can just forget about the mass of the orbiting object and just say something like, just state the constant as that. Now, although up to now I talked about the objects orbiting the sun, you can actually do this separately. For example, you could actually consider moons or satellites orbiting Jupiter and do exactly the same thing, just so long as you keep them separate. You can't mix it up with the previous ones where I've talked about objects orbiting the sun. If I just restrict myself exclusively to satellites orbiting Jupiter, then I can do exactly the same thing. I can set up the ratio t squared or tau squared over a to the power 3 for one satellite and equate it to the same ratio for another satellite and do exactly the same thing. But what I can do using this knowledge is to set up a ratio of the masses of two planets. For example, if I was to consider the satellites around Jupiter, and I was to consider the satellites around Neptune, then the basic equation would be the same. It'd be something like this: G over a again. That's equal to constant. But if I put it in the specific form like this, okay. So I'm setting up this ratio here, but here I'm using a satellite of Jupiter, or I've said here JM for Jupiter Moon. But the idea is that this ratio will be the same for any moon of Jupiter that I choose, and that will equal this expression here. Now, if I do the same thing for a moon or a satellite of Neptune, I can set up the same equation, or not the same equation, but an analogous equation to this. And following on from GCSE mathematics, I can divide this particular equation for Jupiter by the equation for Neptune, like this. I can say, okay, that's T Jupiter of Neptune squared over A Jupiter of Neptune squared. Well, on the right hand side it'll be GMS over 4 pi squared. Sorry. What I'm going to do, hopefully you can understand this, I'm going to take this equal sign there and stick it down here. So if you're not happy with why I've done that, I'm sorry for the way it's a bit wonky here, but if you're not happy with the way I've done that, is that a basic algebraic equation, as long as I do the same thing to both sides of the equation, then that is acceptable. If I take one side of an equation and divide it by 2, and then I take the other side of the equation and divide that by 2, that is an acceptable algebraic operation. So that's essentially what I've done here. I've taken an equation which says A equals B, the left-hand side. Oh, sorry about that. This is saying A equals B, i.e. the left-hand side equals the right-hand side. So if I take the left-hand side and divide the left-hand side of the first equation by it, and I take the right-hand side here and divide the right-hand side of the original equation by it, that is an acceptable operation, because I'm taking the first equation, I'm dividing both left-hand side and right-hand side by the same thing. I'll leave that with you to think about that if it's not immediately obvious. I mean, obviously the advantage with videos is that you can I don't need to go through it to labour the point too much. You can just freeze the video and have a think about it yourself. Now the point is that, again, relying here on basic GCSE mathematics, if you're happy with that, I can just cancel these two out. These are constants everywhere, so I can cancel these out. Cancel them out top and bottom. So that just means that on the right hand side here, I've got so on the right hand side I've got the ratio, the mass of Jupiter divided by the mass of Saturn. So you can see what I've done here. I've used Kepler's third law for individual satellites. So I've got the ratio up for an individual satellite of Jupiter, the ratio for an individual satellite of Neptune, and then carrying out this division, I can actually work out what the ratio is of the mass of the planet Jupiter itself to the mass of the planet Saturn itself. Obviously, if for example I knew what the mass of Jupiter was, I could use this equation to work out what the mass of Saturn is, and so on. But that takes us about as far as it takes it in GCSE astronomy. So that's all you need to know, if you can have a think about that. Now there's just one little rider to all this, or one simplification. The t squared over a cubed. Now, if I was to think of that for the planet Earth, I'm back to the original scenario now, planet Earth orbiting the Sun. So, getting up this ratio for the planet Earth, if t is given in years, then that is just 1. Okay? It takes 1 year to orbit the Sun. If I use this distance in terms of astronomical units, okay? An astronomical unit is the distance from the Earth to the Sun. So if I measure a in astronomical units, that will be 1 as well. So that will just be equal to 1. So the point is that if I use years and astronomical units as the units, then this ratio will just be 1. So obviously I'm restricting myself to objects orbiting the Sun here. But I can then use that fact to simplify the algebra for trying to find out any relevant information for an arbitrary object orbiting the Sun. So any old object orbiting the Sun given by this t squared. I'll call this object x. Okay, any arbitrary object will obey this rule, and that will just equal to 1. So that simplifies it. Just so long as you realise that this time must be given in years and this distance must be given in astronomical units. So yeah, that's all you basically need for GCSE astronomy. I say all, but I mean, I think with a bit of thought, it's although it looks difficult, it's much easier than you might think, hopefully. Thanks for keeping with me anyway. Cheers for now.